This is the lecture video for number 100, What is Global Warming content page. Please make sure you have the note sheet that I made for you to take notes on, so you don't have to do it on a separate piece of paper. So we're going to talk about weather, climate, and greenhouse gases. I'm going to move pretty fast so that this video isn't very long, but remember you can pause, rewind, and rewatch as you need to take your notes. The first thing we're going to distinguish between is weather and climate. This is all about time. Weather is a state of the atmosphere at some point in time, some place and some point. Usually they talk about this in terms of temperature, air pressure, humidity, wind speed, direction, precipitation, and cloudiness. Climate is the average. It's long period of time. It's what it's usually like at certain times in certain places. There's different kinds of climates we have. We have tropical, dry, temperate, continental, polar. Think about New Jersey. If I ask you, what's it like in the summer? You'd probably say it's usually hot and humid. Now, that doesn't mean that we can't have a cold day in the summer. The weather can change quickly, and it's variable by day to day, but climate is generally the average. It's what it's usually like. Now, some people say, like, oh, we're having a hot day in the winter. So much for climate change, so much for global warming. That's not really correct, because the weather can change drastically. Now, if you have 20 straight years where the winter is really hot, like 80-degree days every day, then that is a change in climate. But weather can change randomly. It can change day to day. So let's look at two examples. In Utah, during the day, it's partly cloudy, temperature around 40 degrees Fahrenheit, winds shifting north. If you look at this example, clearly this is talking about weather. It's one day, specific day of weather. If you look at the example on the right, it says that Utah has hot, sometimes extremely hot summers, warm to cool winters, with some minimal precipitation. This is clearly talking about climate, what it's usually like over long periods of time, the average for a certain time of the year. If you track the weather for long enough, you can get the general climate of a place. So if you're going to go to Utah in the summer, you can probably expect it to be hot, right? Now, that doesn't mean that when you're in Utah in the summer, you won't get like a random cold day. The weather can change, but the climate is usually the average. Let's talk about the greenhouse effect. This is a process that occurs when gases in the atmosphere trap the sun's heat. Now, it's not a bad thing, but it can be. Because without the greenhouse effect, the Earth would be frozen and lifeless. We need some of those greenhouse gases in our atmosphere so that, the temperature is warm enough for living things to exist, to survive. Now, if we have too much of it, it can get too hot, or too little greenhouse gases, it can get too cold. So just the right amount is what we want. And the greenhouse effect, essentially, solar radiation comes and hits the planet. Now, since the sky, the atmosphere, the gases in the atmosphere are clear, they don't absorb that UV radiation, but the ground on the Earth does. Now, some places reflect it, but some absorb it. And when the ground absorbs it, it radiates heat. The ground gets hot. That is what heats up the gases in the atmosphere. Now, if we have more greenhouse gases, we have more heat that's able to stay in the atmosphere. Less means less heat that's able to stay in the atmosphere. And we're going to talk about 5 different ones: carbon dioxide, water vapor, methane, fluorocarbons, and nitrous oxide. I'm going to go pretty quick here too. Now, carbon dioxide is CO2, water vapor is H2O, methane is CH4, nitrous oxide is N2O, nitrous oxide, and fluorocarbons are HFC, CFC, and HFCFCs. Lifespan: carbon dioxide usually stays in the atmosphere 300 to 1,000 years. Water vapor, less than 2 years. Methane stays up there for about 12 years. Nitrous oxide stays for a whopping 273. Oops, sorry. I was thinking of the next one. It's 120 years. And fluorocarbons is 50 to about 150 years. Now, global warming potential. GWP is a measure of how much energy 1 ton of a specific gas can absorb in a period of time. It's how much heat this gas, 1 ton of this gas, can hold on to for about 100 years. Now, they use carbon dioxide as the reference gas. So the amount of heat that the gas can hold, it's relative to CO2. So they compare it to CO2. So let me use methane as an example. So they give CO2 a GWP of 1. Methane has a GWP of about 27 to 30. Nitrous oxide has 273. What that means, let me use some arbitrary numbers just to simplify this. Let's say 1 ton of carbon dioxide can raise the temperature for 100 years by 1 degree Fahrenheit. That means that methane can raise it by 27 to 30 degrees Fahrenheit. 1 ton of methane can raise it 27 to 30 degrees Fahrenheit for 100 years. That would mean that nitric oxide can raise it by 273 degrees. Now, I'm just making this up, but that's how it works. That means that compared to carbon dioxide, methane can heat the atmosphere 27 to 30 times more, and nitrous oxide can do it 273 times more. Now, water vapor, since they, you know, do GWP, they measure it based on 100 years. Well, water vapor can absorb lots of heat. So we just write that, can hold lots of heat. But since it only lasts for about 2 weeks or less than 2 weeks, they don't really give it a GWP because it doesn't last for at least 100 years. All right. And fluorocarbons, they have a very high GWP, but still, these are kind of a different sort of molecule. We'll see that in a second. They work a little bit differently. They don't really work by holding heat, but they break down ozone, so they let in more UV radiation. We'll talk about that in a second. So, what is carbon dioxide released by? Well, by producing power. Anytime we make energy, like, we burn fuel, if we do combustion, we're going to release CO2. So, any kind of cars, buses, any transportation releases CO2. Now, some people say, well, what about electric cars? We can solve it that way. Yeah, but most of the electricity on our planet is produced by combustion, by burning fossil fuels. So even though you're using electricity, in order to get it, you had to release CO2, unless we use renewable sources, which we'll talk about next year. Now, water vapor, we can just say the water cycle. We know how water gets evaporated and gets released to the atmosphere. Methane, usually methane is mostly it's from decomposition. Anytime something breaks down, organic matter breaking down. So any dead stuff on the planet that gets broken down by bacteria, they release methane. Even cows, when they eat grass, their stomachs have beneficial bacteria in them, and they pass that grass back and forth to different stomachs they have. The bacteria help break it down. When they burp, they release methane. Wastewater treatment, all of our toilet water that goes to a facility, they use microorganisms which decompose it, and they release methane. Any kind of farming practices like that have soil and dying plants. Now, something that is also interesting, we talked about permafrost. Now, permafrost has a lot of methane in it, and if it melts, it can all release. And you might say, well, how does ice have methane? That's because a long time ago, before there was ice on our planet, there was a lot of grasses and plants. Now, as the planet cooled, and as those plants took the CO2 out of the air, cooling down the planet, ice formed, which killed the plants. And all the bacteria that were there decomposed all that living stuff under the ice. And they're producing methane. That methane couldn't get out. It was stuck under the ice. So there is a ton of methane stuck under all this glacial ice and all this permafrost. And if that permafrost melts, which it kind of is right now, it's very dangerous because that methane has a high GWP. Now, nitrous oxide comes from production, especially in the production of fertilizers. So as more farming is happening and more fertilizer and chemicals are used in farming, which is the modern way to do it, we're making more nitrous oxide, which is very dangerous. Now, fluorocarbons are much different. These are released by aerosols, refrigerators, and like AC units. So let's visualize CFCs. Normally, the ozone layer, which is made of O3, ozone is O3, a bunch of oxygen, O3 of them together, that are absorbing the solar radiation and blocking a lot of that from hitting us, so it's not too much solar radiation hitting the Earth. Now, normally what happens, let's look at this ozone molecule. The solar radiation will hit this molecule, and it'll break it down and it'll form O2 and O. And that blocked the radiation. It absorbed it in its bonds, it broke those bonds, and so that just blocks some solar radiation for us. Now, what's cool is that this O2 and this O can interact with each other and become, again, O3, reform ozone. So this can keep happening. These O3s are breaking down, then reforming and protecting and blocking us from solar radiation. Now, CFCs, which is carbon, chlorine, and fluorine, As we release those from aerosols and they get into the stratosphere, the sun radiation hits them too and breaks all these bonds and releases a Cl. This Cl, this chlorine, is what can do a lot of damage. So what will happen is if the Cl comes up into the ozone layer, it will bond with an O on the O3 and remove it. Essentially, it just broke down the O3, preventing it from being able to absorb any solar radiation, and it made ClO. That's bad in itself, but as this molecule doing its job is absorbing solar radiation, becoming O2 and O, if a ClO is around, it will bond with that O, it'll free up the Cl and turn that, as it bonds, into another O2, and what that means is that now that chlorine is free again. It already broke down one ozone molecule, turned it into O2. It prevented another one from reforming, and it's going to keep going. It'll attack this molecule, breaking this bond, making ClO and O2, destroying that ozone molecule. And then as this one naturally breaks down, blocking some solar radiation, making that O, the ClO will react with that, forming an O2. See these two O's break off, making an O2, freeing up the Cl. And the process continues. It'll hit this one. I'm going to fast forward a bit. Making ClO and O2. Then as this one blocks some solar radiation, becoming O and O, the Cl can attack this one, making Cl and O2. And essentially what you're left with, instead of all those O3s absorbing solar radiation, breaking down and reforming, now there's just a bunch of O2 up there. Now this O2 could get hit by solar radiation and make an O and reform ozone, but this chlorine, just one single chlorofluorocarbon, can just keep getting recharged and breaking down all the ozone. So the more that we put up there, the more that it's breaking down the ozone and creates what we call the ozone hole. Now these HFCs, CFCs, a lot of these were used since they're I think invented in 1928. They were used a lot in the 50s, and they were actually made illegal to put in aerosol cans in the late 70s because they realized how powerful they were at breaking down ozone. And so even after they made them illegal, we still today have an ozone hole. That ozone hole started to develop during the 70s when they realized how bad the HFCs are, CFCs. They made them illegal, and we're still seeing the effects of that. The hole has kind of now stabilized, but it's a good thing that we made them illegal before, because since they can stay in the atmosphere for 50 to 100 years, they are still up there damaging the ozone layer